Hello everyone, my name is James Pruitt and this is my sixth lecture on generating functions. Last time we left off we were talking about if two sequences has a product that is invertible and their generating functions, we're going to call them A and B, and their product is invertible, so that's going to tell us that AB times 1 over AB is equal to 1. And we also had a theorem last time that says that if the product of A and B is invertible, then A is invertible and B is invertible. So that says that we can multiply these inverses like that, 1 over B, and then we can multiply times A times B, and then we can we're dealing with a commutative ring which has associativity and commutativity, so that gives us 1 over A times A, 1 over B times B, and that's equal to 1 times 1, which is equal to 1. So what we've proven is that 1 over A, the inverse multiplicative inverse of A times the multiplicative inverse of B, is the multiplicative inverse of A times B. And we also have another fact from commutative rings, is that the multiplicative inverses are unique. So that says that 1 over A times 1 over B is equal to 1 over A times B. And that's all I want to talk about multiplication right now. Now we want to get on to addition of fractions. So if we have A over B plus C over D, when we write something like this, we make the assertion that B and D have multiplicative inverses. That is, B and D have a non-zero constant terms. So we can't write something like that. That's not allowed, because X doesn't have a multiplicative inverse. Okay, so I want to write something like, I want to do this. I want to say A times D over B times D, and we can write that out as 1 over B times 1 over D times A times D. So we can commute and associate, and we get 1 over B is 1 over D times A, and that's equal to A over B. So we can rewrite this equation here. Let me see if I can squeeze this in here, so that we can rewrite that as A times D over B times D plus B times C over B times D. And we know that a commutative ring has the distributive property, so I can distribute out that B over D. So that's 1 over BD times AD plus BC. So that gives us, the result gives us how we'll define addition of fractions. A over B plus C over D is equal to AD plus BC over BD. So that's what we're going to, that's how we'll add fractions. So we're going to leave the generality for now, and we're going to go to something specific. I want to compute the multiplicative inverse of 1 minus 3x plus 2x squared. And the only way I can do that right now is to go to that theorem I proved, that if a sequence has a non-zero constant term, then it has a multiplicative inverse. And I described a process by which you can construct a multiplicative inverse. And that process, and I'm going to follow that process right now to compute the multiplicative inverse of this guy right here. So the first step is to get rid of this 3x. So I multiply by a 3x. So I say 1 plus 3x times 1 minus 3x plus 2x squared is equal to 1. The 3x's are gone. Then we got 1, and we got a 2x squared here, and then a 3x and a 3x. So we're going to get a negative 9x squared plus a 2x squared, and that's going to be a negative 7x squared. And then I got this 3 times 2 is 6 plus 6x cubed. I think I multiplied that right. So if I go 1, negative 3x, 2x squared, and then I go 3x, and then I go negative 3x squared, and I go 6x cubed. Okay, yeah, that's right. So next step is to get rid of this 7x 7x squared term, the negative 7x squared term. So I do that by multiplying by 1 plus 7x squared times 1 plus 3x, okay, times 1 minus 3x plus 2x squared, and that's going to equal to, okay, the 7x squareds are gone. 7x squared times 7x squared is negative 49x to the 4th, so we still got that 6x cubed that comes before that. Then we got the negative 49x to the 4th, and then we're going to get 7 times plus 42 x to the 5th. Okay, so we got 1, 2, 3 terms here. 1, 2, 2 times 3 is 6, and we subtracted 1 off, so that should be 5 terms. 1, 2, 3, 4. Let's see where I goofed off. 1, 2, 3, 1, 2. Okay, we have some overlapping. Yeah, so yeah, that's right. That's right. Okay, so now I want to get rid of the 6x cubed term, so I have to multiply by negative 6x cubed times 1 plus 7x squared times 1 plus 3x times 1 minus 3x plus 2x squared. Okay, so that's going to equal to 1. The 6x cubes are gone. Let's see what we got. A negative 40. 6 times 6 is 36x to the 6. So we got to pull down everything before the x to the 6th term. Minus 49x to the 4th plus 42x to the 5th. Now we got minus 36x to the 6th. Then we got 6 times 49, and I don't know what that is. 6 times 49 equals 294, and that's a negative 6 times a negative 49, so that's a positive 294, and it's x to the 4th, so it's x to the 7th. And now we got 42 times 6. 6 times 42 is 252, and that's positive 42, negative 6, so we got a negative 252 x to the 8th. So I'm going to stop right here, and so because this process is going to go on, it seems to me, forever. So what we've done, we're in the process of constructing the multiplicative inverse of this guy. So this product is a partial construction of the multiplicative inverse. So we're going to follow the pattern I've talked about before. I'm going to multiply that out and see if I can see some sort of pattern to get an educated guess of what the actual multiplicative inverse is. And then I will do the multiplication and see if I get the multiplicative identity. So here it goes. So I go ahead, let me see what time we... Okay, so here it goes. Let's see if I can do this in a timely manner. 1 minus 6x cubed times 1 plus 7x squared times 1 plus 3x is equal to 1 minus 6x cubed times 1 plus 3x plus 7x squared plus 21x cubed. And then we come down here and we're going to get 1 plus 6x cubed times x is 3x is negative 18x to the 4th, so we just got to bring down all the ones before the x to the 4th term. So it's plus 7x squared plus 21x cubed. Actually, we got an x cubed here. So here so this guy's going to contribute some to this term. So we got a 21 times 21x cubed minus 6x cubed times 1. So that's 21 minus 6 is 15. 15x cubed. And then we negative 6x cubed times 3 is negative 18x to the 4th. And negative 6 times 7 is negative 42 x to the 5th, and negative 6 times 21 is negative 126 times x to the 6th. Okay, let me see what we got on our times. Okay, Now if we look over here, we're in the process of our next term, our next product we're going to do to eliminate this term is I'm going to multiply 1 plus 49 x to the fourth. And when I multiply this term right here times 1 plus 49 x to the fourth, that product will not touch this, it will not touch this, it will not touch this, it will not touch this. It will only affect the terms up from here on over. So these terms from x3 on down are static. These are not going to be changed when I multiply this polynomial by 1 plus 49 x to the fourth. So we can go ahead and let Bn be my guess. Be my guess for the multiplicative inverse. Okay. So we can go ahead, and since we know this is static, this is going to be the actual, this is going to be in the multiplicative inverse. So the multiplicative inverse are going to have these terms. So I'm going to say B0 is equal to 1, B1 is equal to 3, B2 is equal to 7, and B3 is equal to 15. So I can look at that and I see a pattern, Bn, and it looks like it's 1 less than a power of 2. So it's equal to 2 to the n plus 1 minus 1. So if B1, if I put a 1 here, that's 2, 4 minus 1, 2 to the 3 is 8 minus 1, 2 to the 4 is 16 minus 1, so that all checks out. So now all I got to do is multiply and see if I get the multiplicative inverse. Let me go ahead and write this as 1 minus, this is what we're trying to take the multiplicative inverse of, plus 2x squared, and so a naught is equal to 1, a1 is equal to negative 3, a2 is equal to 2, and an is equal to 0 for n greater than 2. Okay, so there's only 3 terms with this an, so I'm only dealing with 3 terms, so it's going to be easy. So I'm going to let, so we'll let Cn equal to an times Bn. And so B naught, trying to get too fast. So C naught is equal to A naught times B naught, which is equal to A naught is 1, B is 2, 0 plus 1 minus 1, and that's equal to 1. So that's times 1 is equal to 1, which is good. Okay, C1 is equal to A naught B1 plus A1 B naught. So that's equal to A naught is 1 times B1. So B1 is 2, 1 plus 1 minus 1. So that's 4 minus 1 is equal to 3. Is that right? B1 is equal to 3. So that's times 3 plus A1 is negative 3. Negative 3 times B naught, which is we already calculated, is 1. Okay, so C1 is equal to 3 minus 3 is equal to 0, which is good. Okay, so now we come to, I'm just going to ahead and go with Cn. Cn is equal to A0 times Bn plus A1 times Bn minus 1 plus A2 times Bn minus 2. Now we're out of A2s. The rest of the Ans are 0, so they're going to cancel everything out, so it's not going to contribute. Okay, so that's going to give us, that's going to give us, I'm going to have to watch the time real quick, that's going to give us Cn is equal to A0 is 1, Bn is 2 to the n plus 1 minus 1 plus A1, which is negative 3, times 2 to the n minus 1 plus 1, and I'm going to stop right here, and I'll pick up right here next time. Thank you.